Okay, let's review Introductory Organic Chem in class exercise 1. For the first question, you are being asked to, from a pair of organic compounds, which of them contain the same number of hydrogen atoms? So basically, this question is to allow yourself to be familiar with skeletal structure. Okay, so maybe a quick review of skeletal structure is that if I have a zigzag structure like this, I will be able to do a count from left to right, 1, 2, 3, 4, and each of them should contain a carbon atom. And then the number of hydrogen depends on the bonds being formed around that carbon. So for carbon number 4 and 1, there's only one bond being connected to carbon 3 or 2. So therefore, the remaining 3 sigma bonds must be bonded to H. So there will be 1, 2, and 3 H's at the end. Okay, then for carbon number 2 and 3, because each of the carbon is sigma bonded or singly bonded to 2 other carbons, so the remaining 2 single bonds must be bonded to hydrogens. Okay, so there will be 2 at carbon 2 and 3. Okay, so from here you realize the formula for an alkane, because this is butane, is CnH2n plus 2. The plus 2 simply means that the 2 carbon at the end, okay, will have an extra H. Yeah, so when you have a cyclic compound like a cyclobutane, that will mean that the 2 ends, in this case between 1 and 4, is now being joined up like this. Okay, so we'll have 1, 2, 3, 4. And because when they join up, carbon 1 and 4 forms an extra single bond. So therefore, the formula for cyclobutane is now CnH2n. Okay, so you realize that from this pattern that whenever you form a ring, okay, or you form a double bond, the number of hydrogen decrease by 2. Okay, so that also means that the number of hydrogens, right, for a compound containing carbon and oxygen can never take on an odd number. Okay, of course, with nitrogen, you can take on odd number. That is not an issue. Yeah, but that's another discussion which we won't be discussing over here. Okay, so in this case, let's do a quick count. So we have 3 carbons here, so we'll have 3 H's at the end, 3 H's at the end, 1 in the middle, 2 here. So that will be a total of 9. Okay, and the one on the right is 3 methyl group. The middle carbon is what we call quaternary, so there won't be any hydrogen. So that's also 3 times 3 equals to 9. Okay, so 1 will be an option we can choose. Okay, for option 2, these are 2 ethyl groups, so 1, 2, and 3 hydrogens, and then 2 more over here. Right at the end is symmetrical, so that's 2 times 5, 10 hydrogens. Yeah, so over here there's 1 hydrogen here and 1 hydrogen here, so that's 2. And then in the middle, 3 bonds, so there's 2 hydrogen each, so that's another 2 more. And then you have 2 methyl group, that's 6. So if you add them up, it's 10. Okay, so in that case, I will also give option 2 a tick. Okay, for option 3, if you do a quick count, you have 3 hydrogens here, 2 hydrogens here, and then another 2 here. So that will be a total of 7. Okay, and then over here there will be 1 hydrogen here. So this is an aldehyde. Normally the hydrogen tends to be missed out. So in case you are afraid that you will miss it out, please draw it out on the diagram. So there's 1 H here, and then there's 1 more H at isopropyl, and then the 2 methyl group right at the end. So that's 3 times 2 plus 2, that's a total of 8. And because 8 is not 7, so I will not choose option 3. So in the end, my answer will be B. Okay, and then for the second question, you were told that this particular setting agent for a chocolate mousse is actually an organic acid. Yeah, so at your current level, an organic acid, usually you will think of it as a carboxylic acid, although it need not always be the case. Okay, so just take note that it could be a carboxylic acid. So if it's a carboxylic acid, in that sense, that will mean that I need to have a carboxylic acid group over here. So for a carboxylic acid group, if you do a quick count, the MR is 45. So that's 12 plus 32 plus 1, so that's 45. And because it's dibasic over here, so you would expect 2 units of 45, that's 90. So I will take 146 minus 90, so I'm going to get 56. So that means that the remaining carbon and hydrogen combined together, there will be a total MR of 56. Okay, there are several ways you can go about doing this. I think first you were told that it's non-cyclic. Okay, so therefore it's straight chain. It doesn't contain any CC double bond, so that means that this 56 must be saturated. Okay, I mean, of course, saturated in a sense, just that middle portion, because the carboxylic acid group is definitely not saturated due to the C double bond O. Okay, and then the MR, I think we have used this particular data. Okay, so one way you can go about doing that is that you can just take 56 divide by 12. That 12 is the relative atomic mass of carbon, so you will get about 4 plus. Okay, 4 dot, 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 dot. So that's about 4.6-ish. Okay, then you know you can't take the upper limit because between 4 to 5 you can't take 5, because if it's 5 it exceeded 50, it will exceed. If you incorporate extra hydrogen, it will exceed 56. So if it's 4, that will be 48. So that will make a little bit of sense, because if it's 48, you have C4, and then the remaining will be H8. Okay, so that kind of makes sense. That will mean that the middle could be a mixture of CH2, or it could be branched. Okay, so one possible structure, as I've shown in class, it will be a straight chain that looks like this. Okay, or I can have it branch, which could look like this. Okay, so I could have it branch, that's 1, 2, 3, 4. Okay, so yep, these are two possibilities. So whatever the case is, the total number of carbon will be 6. So I will pick 6 as the option. Okay, yep. So for question 3, I have saccharides over here. So I have ribose and glucose. So if you do a quick scan through the functional group, because that's the question being asked here, you will realize that there's an aldehyde group over here. So remember earlier on I mentioned that if you are unsure, you can always draw out the H for you to confirm that it's actually an aldehyde group. Okay, because I don't think I mentioned that in the lecture, but for aldehydes, the difference is that it contains a H instead of other groups. Okay, so maybe I can do a quick summary. Yep, so normally if let's say I have a R group on the left hand side and I have a C double bond O, this portion, right, I will call it the carbonyl group. Okay, so maybe let me write it out. This is called the carbonyl group. Okay, so the carbonyl group is a special group. It's a C double bond O, and so on the left and right it can bond to other things lah. So normally for nomenclature wise, on the left hand side, let us begin with having an R group, or what we call an LQ group, and then on the right hand side I can have X. Okay, so X can take on several identity. If X is a H, then this compound will be called an aldehyde. Okay, if X is an R group, this compound will be called a ketone. Yep, if X is something that is familiar, let's say an OH, and we'll call this compound a carboxylic acid. Okay, and of course another thing which you learn in secondary school is that X could be OR, and we'll call this compound an ester. Okay, and then if X is, let's say, a NHR, we'll call this compound an amide. So this should be something that is quite familiar from secondary school, at least carboxylic acid, ester, and amides. Okay, you would have learned ester and amide under the polymer chapter. Okay, so right now we'll go into the functional group. So we have an aldehyde there. Okay, then Next, while we're having, you notice that the one right at the end is an alcohol that's bonded to a CH2. So we will call this a primary alcohol. And then in the middle field, you have an alcohol that's bonded to a CH. So all these are called the secondary alcohol. So in this case, what we have is a primary alcohol, okay, a secondary alcohol, okay, and of course, finally, we have an aldehyde, okay, which makes up the two monosaccharides. Then for part B, you're supposed to suggest the general molecular formula for a monosaccharide with n number of atoms. If you do a quick scan across these two, right, you notice that they follow a relatively similar pattern. So for the left hand side, for ribose, you have a total of 5 carbons. If you do a quick scan, there will be a total of 10 hydrogens here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you have 1, 2, 3, 4, 5, 5 O. Yeah, and then for glucose, it will be C6H12O6. Okay, so for the general formula for the monosaccharide, you would expect it to be CnH2nOn. Okay, then finally for part C, you have two glucose molecules undergoing condensation to form a disaccharide maltose. Take note that for condensation reaction, there is an elimination of a water molecule. So the question is, they ask you to suggest the formula for maltose. Okay, so one way to go about doing this question in a simple manner is to write out the formula for glucose. So when you write the formula for glucose, that will be C6H12O6, and then you add the two formula up together, then you end up with C12H24O12, and then finally you are required to eliminate a water molecule from here, so you end up with C12H22O11. So this will be the formula for maltose, C12H22O11. Okay, yep. So that's about it for question 3. Next, we look at question 4. So for question 4, you have a reaction scheme depicting some reaction involving compound X. So for compound X, if you look at the first reaction, you realize that the double bond is gone, okay, and the Br actually adds across the double bond over here. Okay, some of you might be wondering what exactly is CCl4, why is that a slash? So this CCl4 is actually the solvent. Okay, so in organic chemistry, usually when we have an arrow, we will write the reactant on top of the arrow, and then we'll write the conditions below the arrow. This is usually the case. So the condition could be the solvent we use, the temperature, the pressure. Okay, but if we have weird looking arrows like slanted or this, sometimes we'll just put a slash or we put a comma. So it's really up to us to interpret. Okay, so obviously this is a form of addition. So for 1, it will be called an addition reaction. Okay, then for 2 over here, you realize that Cl is being replaced by OH over here. Okay, because it's something like a 1-for-1 replacement. So similar to secondary school, we'll call it a substitution reaction. Okay, so this will be a substitution. Okay, and then for reaction 3, if you recognize this familiar friend, this is actually an oxidizing agent, so KMnO4. And then you realize that in the course of the reaction, the OH we say over here is being added, but we cannot call this an addition, because in fact what exactly happened is that the carbon gets oxidized. Okay, so we'll call this an oxidation reaction. Okay, how do we know that the carbon gets oxidized? So if you recall what we did in the stoichiometry tutorial, so I'll just do a quick recap over here. Let's say we have an alkene over here, ethene, right? So if we were to do a quick calculation of the oxidation state of carbon over here, so I'm just going to draw the dot cross diagram very quickly over here, right? So if we assume a perfect ionic model, carbon being more electronegative than hydrogen, it will take all the electrons. So we just do a boundary like this. Yeah, so originally carbon has 4 electrons, now it has 6. So therefore the oxidation state for carbon is -2 over here for ethene. Okay, then if you subject this to a reaction with MnO4 minus under the same condition, the co-alkali condition, and I end up with a diol, right? So what I'm going to get is, let me just sketch out very quickly the dot and cross diagram. You end up something like this. So you have an O here and then blah blah. Okay, I'm not going to sketch the rest. Okay, and then cross dot. Okay, so if we assume a perfect ionic model, so I'm just going to draw the boundary. It will be like this and like this. Okay, like this. So you do the same thing, you do a quick calculation. So there will be 1, 2, 3, 4, 5. 5 electrons over here instead of 4. So the oxidation state increases to -1. Okay, so from -2 to -1. So this is indeed an oxidation. Some students might be asking, what about the H? There is an addition of H, right? Okay, so the H actually remains as +1. The H actually comes from water. It's actually part of the system in the oxidation reaction. Okay, so if you are still puzzled about it, we can always discuss more in the tutorials. Okay, and of course, this particular H is very different from this hydrogen here because this particular hydrogen has an oxidation number of 0. Okay, so from 0 over here, it gets reduced. I mean, the hydrogen gets oxidized, but the CC double bond gets reduced. So now the H comes into here. So this is some form of catalytic reduction. Okay, so the answer to this will be reduction. Okay, you can now say that the carbon here gains hydrogen where the original oxidation state of hydrogen is 0. So in this case, hydrogen gas gets oxidized and carbon gets reduced. You can do a quick calculation if you want over here. You will recognize that the oxidation state of carbon reduces by 1. Okay, you can verify it easily yourself. Okay, for catalytic reduction, we can also view it as some form of addition. You can view it as the addition of hydrogen across the CC double bond. Alright, so that will be the end of the review for exercise 1.